Welcome to EDU World Space.
So we have a circuit with a battery that has an EMF E and internal resistance R, and to this battery, a resistor of resistance R is connected, and the power output of the battery is P, and because energy is conserved, P is also the power that's dissipated by the resistor. And in part A, we're asked what is the value of P in the limit that R is small. So we have to find the power when R is small in part A. So what we can do is first write down an equation that relates uh, the things that are given. So we're not given I, but we're given the EMF, the resistor, and the internal resistance. Um, and from here we have that the we can so let's do this. So we have this equation that relates to quantities that were given except for I, but we can use P is equal to I squared R. And then if we solve this equation for I and then substitute into here, then we would have eliminated I, and then we'll have the power in terms of only the things that were given. So we'll solve this one for I. That is E over R plus R. And if we substitute that into this equation, then we get that P is equal to E squared R over R plus R squared. And actually, throughout this problem, we'll be making use of this equation. So now in part A, they're asking what happens when R is small. So that's basically saying, okay, we take the limit as R goes to zero, right? So R is getting smaller and smaller and smaller. So in that case, when R goes to zero, the denominator gives us just the internal resistance, but the numerator goes to zero. So in that case, as R goes to zero, so does P. So as R gets smaller, P gets smaller. Okay, now let's go to part B. And part B, we're also asked, okay, what happens to P when R is very large? So let's write down the previous equation that we have, that P is E squared R over R plus R squared. And now we want to know what happens when R is getting bigger and bigger. Well, if R is getting bigger and bigger, the denominator is R plus R squared, but if R is bigger and bigger and bigger, then R is going to be much greater than R, right? So that R plus R is approximately R, because this is very small in comparison to this. So then your denominator just goes to R squared, and your numerator, well, is just epsilon squared R. So P now in this case, as R goes to infinity, is over R squared, which is But as r goes to infinity, right, you're dividing this by a bigger and bigger number, so that actually goes to 0. So in both cases, we call them the limiting cases. As r goes to 0, p goes to 0, and as r goes to infinity, p goes to 0. So at either end, basically you have p going to 0 when r is very small, and p goes to 0 when r is very large. In part C, we're asked to show that the power output of the battery is a maximum when R is equal to the internal resistance. And what is this maximum P in terms of E and the internal resistance? So this part of the problem is a little bit tricky, and I'll actually use some calculus to solve it. So let's go to a new page. And again, we're going to write the equation that we had before, where we have e squared r over r plus r squared. Now, I'm going to do something a little funny. So what I'm going to do is kind of factor out and this internal resistance from the denominator. So if I factor it out, then I have an r squared, and then I have 1 plus r over r all squared. And I'm going to rewrite this a little bit as a factor of, let's say we have e squared over r, and then I have over here r over r, and then I have 1 plus r over r squared. And this may look a little funny, but there's a particular reason why I'm doing this, so that I can write this in a simpler form, although this looks a lot more complicated than what we started with. But remember that as you're changing R, E, your EMF, and your internal resistance, we're assuming that those things are remaining constant, right? So this is a constant, and let's call it A, for example. So let's call it something else, so we don't have to carry around all this bad notation. So we're just calling it A, which is a constant. And then let's define R over R, the resistance over the value of the resistor over the internal resistance. Let's call that X. So right, so we have now written the power. So we have the power is equal to A x over 1 plus x squared, where A is the EMF squared over R, and X is the resistance of the resistor over the internal resistance of the battery. And so what we'll do now is use some calculus to find out what the maximum of this thing is, right? So when you want to find the extremum of some quantity, you take the first derivative of that thing with respect to the quantity, and you set it equal to 0. So for example, dp dx is equal to 0, right? And so if we take the derivative of this thing, we get? Well, a is a constant, so it could come out. And basically, we're taking the derivative of x times 1 plus x to the minus 2. And if you carry that out, then of course, that was equal to 0. So this is like the prescription for finding the extremum, so maximum or minimum. So if you carry that out, then you have a, right, times, here I have 1 over 1 plus x squared minus 2x over 1 plus x to the third, and that's equal to 0. And so if I move this guy to the other side, so remember a multiplies everyone, so then I have 1 over 1 plus x squared is equal to 2x over 1 plus x to the third. And if I multiply both sides by 1 plus x squared, then I have 1 is equal to 2x over 1 plus x. And then if I move the 1 plus x to the left side, then that gives me 1 plus x is equal to 2x. And then if I subtract x from both sides, I have x is equal to 1. Let's go to a new page. So I've found that x is equal to 1. And at this value, we get the maximum power. But recall that x is actually defined as the resistance of the resistor over the internal resistance of the battery, and that's equal to 1. So that tells me that the resistor of the battery, the resistor of the resistance is equal to the internal resistor of the battery. So this is the condition at which we get the maximum power, which is what we were asked to show in the first place. And we were also asked what the value is in terms of the EMF, E, and in terms of the resistance, R. The internal resistance R of the battery. So let's write P max, right? So the maximum occurs when R is equal to R. That is equal to actually, let me just rewrite what we had before. So we had A, right? And then we had x over 1 plus x squared. And let me put again what these things are. So A was E squared over R, and then x was R over R, and then this is 1 plus R over R all squared. And at maximum, we have this condition. So E squared over R. So R becomes the resistance of the battery becomes the internal resistance. The resistance of the resistor becomes the internal resistance of the battery. So this ratio is just 1, and this is 1, and this is 1. So that's 2 squared, which is 4. So the value is E squared over 4 R. And in the final part of the problem, in part D, we're given that the battery has an EMF of 64 volts and an internal resistance of R equals to 4 ohms. So E is equal to 64 volts. This is part D. And R is equal to 4 ohms. And we're asked what is the power output of this battery when it's connected to a resistor of the value R equals to 2 ohms. R equals to 4 ohms and R equals to 6 ohms. Okay, so we have three things that we have to calculate. And we're also asked if these results are consistent with the general results that we derived earlier. So we can go ahead and calculate these things. So we have P is equal to the EMF squared times the resistance over R plus R squared. So this was the equation that we had earlier. And so all we need to do is for each value of the resistor, we just plug it in here. So remember the EMF and the internal resistance of the battery, they're constant. So those things are not changing. It's just the value of the resistor that's changing. So let's call this 1, 2, and 3. So then P1 is equal to 64 volts squared times R1, which is 2 ohms, divided by 4 ohms plus 2 ohms squared. And that's equal to 227.6 watts. And P2 so that's when R is 4, so you have 64 volts squared, 4 ohms over 4 ohms plus 4 ohms squared. That's outside. That gives a value of 256 watts. And P3 now is 64 volts squared times 6 ohms divided by 4 ohms plus 6 ohms squared. And I'll leave it to you to punch this in your calculator, but you will find that it will be less than P2.